Okie dokie. I'll tell you what, I saw a good example of poor hiring processes this morning at the polls in Grafton. I was in this line for whatever my district was or whatever, and that guy, the volunteer they had working our line, this guy, he had like a hearing aid like the size of a baseball, couldn't hear a thing. So everybody, you're supposed to walk up and say, state your name and your address, so they can find the right person. Did not have a clue what you were saying. Each person took so long. I was in line for 45 minutes just to get this stupid ballot. And he seemed like a really nice guy. But then on top of all that, he wanted to have a conversation with each person. It's like, oh, how have you been? Did you see the sale at Sunday? uh, who knows? Maybe that'll be the most positive, memorable thing about this election was my experience at 6 in the morning. All right. Yeah, I thought about voting early and I decided I would do it yesterday. And then I realized they don't actually, at least in Grafton, they don't allow voting the day before. Must be some law. They have to prep for the real day of election versus the early voting. Yeah. Well, I know my neighbors did it on Saturday, but yeah, I mean, there's some rules. Maybe it's community specific or something, but whatever. It worked out in theory, I guess. I guess it worked out. I was able to fill in some bubbles, and they should have had that guy doing the guide your ballot into the box thing. He could have helped with that. You know, just put it there. All right, so let's keep kicking. We are converting between C++ and Java, right? Started down that line. Let's see where we left off there. All right, so last several classes, we've really been talking about expanded ways of storing stuff, right? So before we had a single variable that could just hold one value. Then we looked at, the ability to hold a collection of same kind of values in things like arrays. If you've worked with Python before, they're not called arrays, they're called lists in Python. When you get into the third coding class, the data structures course, most of those operate with it comes with they're called linear and non-linear linked data structures. So we have something called a linked list. And linked lists, which we're not going to learn about in here specifically, but just to give you an idea, one weakness of an array is once you build the array, you've asked the operating system for, hey, give me 100 bytes of memory to store my array in contiguous memory. Well, once you've done that, and if you want to add one more thing, you got to build a brand new array. So the real life example of that might be like if you have a house and you've bought the house and we'll just pretend like some of the laws with how close you could build to the property line don't exist. You've built your house all the way to the edges of your property line, and now all of a sudden you want to put a deck in. Well, you have to go buy a new house. You can copy everything over from your old house, but you need a house that's a little bit bigger to now, the land to host, to hold your new deck. Make sense? So we would say that in real life, that would never be efficient, but that is how it works in a computer. Once you use an array and once you ask the operating system for some number of bytes of contiguous memory, and it gives that to you, that's your playground. If you need to store more than will fit there, you're going to have to go and ask for new memory, copy everything over from the old memory, and then add your new stuff after that. We can say, well, in real life, that would never make sense. You probably would just not put in the deck, right? But sometimes in computers, you might decide, hey, I'm going to just go ahead and burn down this house and make a new one. And even though it's a waste of memory or kind of slow, computers let us do it. No harm, no foul. Okay. So that's not necessarily a problem. It's just a thing. It's something for us to consider. Well, what if now arrays here, let me actually let's get this onto a slide here. Yeah, we'll put it right after this one. When are arrays a good idea? All right. So we know they already generically solve the problem of holding more than one similar value, like kind of value under a single variable name. That's great. So that's your base thing. But when are arrays a good idea? When we know either exactly how many items we need to store, or we know the max number of items, and it isn't too much of a memory waste because a little bit of a gray area there. So we might say, oh, well, I'm the maximum number we would ever store is 10,000, but maybe the average number you're going to store is 3. So to build an array with 10,000 buckets is going to take up a good chunk of memory, depending on what each of those buckets is built to hold. And if you're on average going to store 3, 4, 5, something like that, but you want to support up to 10,000, you could say, well, an array would be acceptable for that, but you're really going to be wasting a significant amount of space inside the array, and this is space you probably would never use. Punchline is just buy a computer with more RAM. That's the modern way of doing it, right? Just get more RAM, you're fine. But we have an alternative that I'll at least introduce here. We're not going to talk about how they're built. When are linked lists better? So a linked list is an object type, and we're actually going to probably end up accidentally kind of writing a linked list here over the next several weeks in class, but I'm not going to describe it as a linked list. We're going to be creating kind of this dungeon crawler type thing, like they're an old kind of game called a multi-user dungeon, a MUD, where you have rooms and rooms have exits that link to other rooms, and effectively we're going to build a linked list where your map can just grow arbitrarily in size. But a linked list is when we don't know how many items we need to store. And we are okay with a slight performance loss. And for arrays, we're going to say we need speed. So sometimes we might say speed is more important than wasting memory. So we're going to pick arrays and just make them gigantic and keep track of how many things are actually in there. And it's because using an array, that whole idea we've been talking about of going to the base memory address and then taking so many steps through memory to get to the bucket you want, that is very fast. Okay, because that's why arrays require contiguous memory right next to each other. So you can get to the right zone, take a couple of hops, and you're there. So it's fast. You can mathematically calculate your final destination. Whereas a linked list, effectively, antithesis is it does not use contiguous memory. It does not use memory that lives right next to each other in memory. Instead, it says, okay, you want to store one value, we'll put this value here. You want to store another value? No problem. We'll put that over here wherever we found, free memory that could hold it. And we'll just store a way of getting from the first value to the second one, a link. All right. Think of it like a big map with roads. Roads go different places, right? But you got to go to city 1. Then from city 1, you can get to city 2. From city 2, you can get to city 3. So you really have to traverse memory in order to get to those destinations. But the benefit is that you can fit more stuff into a linked list because you're not limited by the amount of memory you have in your computer that's available in a row. You're only limited by the amount of free memory you have in your computer. But the nature of it is it's going to be slower when you traverse it. So when you don't know how many things you're going to store, you might as well just start with an empty list and then just let it grow as you need to fill it with stuff. They are slower, but they're more memory efficient. Arrays are faster, they're more memory inefficient. One is not better or worse than the other one. They're just for solving different problems. Call it 99+% of the time, you're not going to notice a speed difference, regardless of which of those you use. The programs you're writing are, computers are really fast. Okay, so we've been talking about ways of storing data, and storing multiple pieces of data under a single variable name. Then we upgraded to structs and said, okay, well, with a struct, I can now store multiple pieces of data that doesn't have the same data types. I think we used an example like a soccer player. He would have a first name, a last name, a jersey number, maybe a number of goals they scored. You're keeping track of 4 different pieces of information under a single variable name, but those 4 pieces of information don't need to be the same data type. So we would call that, at least for problems that we're solving, that would benefit from us having more granular control over the names of the values we're storing. Structs are an upgrade to arrays. If you're just storing a whole bunch of test scores and you want to figure out what the average is, a struct is not the better tool for the job. You might as well just have an array called test scores, fill it up with all your test scores, and then calculate the average of that. All right. So understand, with all these things we're talking about, it's not that each new thing we talk about is an upgrade to the previous thing. It's what's the right tool for the job you're trying to solve. And like I said, anything that involves speed or memory use, 99% of the time, you could reasonably throw that out the window and just pick the thing you like working with more, because you're not going to notice a speed difference and you got plenty of RAM. So something to keep in mind. All right. So we talked about the new keyword. So this is kind of like our real estate agent goes and gets memory from the operating system for us, regardless of what we're using that memory for. All right. So that's arrays. That's linked list. We talked about structs. All right. So now we get into, well, how do we upgrade from structs? What was the a weakness of structs? Most of our programming languages, when we look at newer languages compared to older languages, we start seeing new features that were added to the language that weren't in the older one, and it no longer was convenient to just add that feature to the old language. We kind of saw that with C++, and you see it with online GDB when there's, like, I don't know, 5 or 6 different C++ things in the dropdown, depending on which version of C++ you want to be, which version of that pinball machine you want to be playing. So eventually it's like, well, we can't really add more to the language. C++ is an object-oriented language. So really we jumped from everything we've done up through structs is really something we could say belongs to the C programming language. Okay, and a procedural, non-object-oriented language. Once we now say, okay, well, you know what, a weakness of structs is that I can only hold name value pairs. I can't hold functions. And now that we're writing a lot of functions and we kind of want to store data that's all related to each other, but different kinds of data like we do with a struct, it would be awesome if I could pull those together under a single pod. So now I have my objects that hold pieces of information about an object, but also have some abilities that object can do. Now, are objects better than structs? Not necessarily. If you're not going to call any functions or write any functions, it's a waste of time. All right. But classes do give us the ability. This goes back to our from week 1 or 2 of class when we looked at the object-oriented version of the telephone versus the procedural version of the telephone. The C programming version of the telephone is the pile of wires. The C++ version of the telephone is the thing that looks like a telephone, yet we know all those wires are in the inside. There's a whole bunch of fields, pieces of data that the phone knows about itself. And then it has a whole bunch of functions, methods, abilities that the phone can perform that also lives inside that plastic. All right. So we can carry that phone around as a single object, and it has both data and function. Make some sense? That's what an object is. So C++ introduced the ability for us to now create objects, for us to do something beyond structs. And I would say that probably covers 95% of what C++ brought to the table from C. Cleaned up a couple of other things, added some syntaxes. We got that little arrow syntax that I think I showed you last class quickly. That came with C++, because you always need more weird symbols. But in any case, that's what C++ brought to the table. So even though this whole semester we've been referencing that we've been learning C++, we've actually been coding in C up to this point with one exception. Anybody who's programmed some before, I probably mentioned it in class before, what has been the only thing we've been using from C++ up to this point? There's actually two things. That is why I chose to use the C++ compiler rather than the C compiler. One thing is strings. C strings suck. You wouldn't like them, and it's not going to teach you what you need to learn to be able to be functional in more modern languages. It's fun because you get to mess with pointers all the time, but it's just not a great use of time. Go back and learn about it historically and that kind of stuff. The other thing was the IO package. Even though I think I mentioned, I actually prefer reading stuff in and writing stuff out to the screen in C. And you can use the C libraries like printf, and in C++, you just include standard IO, stdio.h at the top instead of IOstream. So C++ IO uses IOstream. C IO uses standard IO, which is still available in C++ if you choose to use it. The reason I go with the IOstream stuff is it's most similar to the way people do input output in our more modern languages, even though our more modern languages also support things like printf. Formatted strings, if you've worked with Python before, Python has a normal string and then they have a formatted string, right? Formatted string, what do they do? Before the double quotes, they just put a little F. This is formatted. Treat it as if it's formatted, and you put little placeholders in there. But all these languages are effectively the same. So rather than us get into the some of the, call it transitional details of looking at objects in C++, we're just going to go ahead and jump to Java and start introducing classes and objects in Java. And trust me when I say that it's 97% the same as we would have run into with C++. We're just missing a couple of arrows for some syntaxes. All right, but let's upgrade, keep us uncomfortable, just as you were starting to get a little used to C++. Now we're going to change it on you. Never want you to get too comfortable. All right. So we talked about this idea of the class keyword. So in all object-oriented languages, at least all of them I can think of, whenever we want to make our own object, we use the keyword called class. Just like we've been using the keyword struct to make name value pairs. I mentioned in Python, a struct is kind of something called a dictionary, mostly-ish, because dictionaries are actually passed by address, structs are passed by value. So we have a little idiosyncrasies within those things in terms of how the language is designed. But basically, the class keyword is something that belongs to object-oriented languages, and it is the keyword we use to generate things that store a bunch of name value pairs, and then they also potentially have abilities. And we talked about at the end of class last time that the things that a class might hold. So when you go to the store, you come home from Home Depot and you've got your, do-it-yourself at home class kit, right? You open that up. There's 3 different kinds of things that live inside of classes. We have things called fields. Fields are our variables. So, like when we were dealing with our struct fraction, right? We had a numerator and a denominator, 2 values we were storing. Those would be fields if we had a fraction object. All right. Then we have constructors. These are the guys that we use to build those instances of a class. And we've been kind of doing our own constructors up to this point. So if we go back to, well, let me just switch this over to, you know what? Actually, I'll write the code here real quick, even though we're not going to run it. Okay, so we're running in Java here, but let's say I had something, structs do not exist in Java, but I'm going to write it here anyway. So let's say we had our struct fraction. Try to complete stuff for me. And inside here, we had an int numerator and an int denominator. All right. And then down here, we might say, okay, well, we're going to have a struct fraction f1. And then we're going to say f1 dot numerator is equal to 1. F1 dot denominator is equal to 2. So effectively, we've generated a fraction like this. If we wanted to build our own function that kind of behaves like a constructor in the future will behave, we might say, you know what, it took 3 lines of code here for me to fill up my fraction. And it's just kind of out there. Whenever I build a fraction, I'm going to provide a numerator and a denominator that's going to give me a fraction. So we might say, well, let's go ahead and create a function. Maybe this guy returns a struct fraction. And it's going to be called make fraction. Maybe it takes an int numerator and an int denominator as parameters. And then inside here, it'll say struct fraction, call it answer. Answer dot numerator is equal to the numerator that was passed in. Answer dot denominator is equal to the denominator that was passed in. And then return answer. All right, so here's a function called make fraction. In fact, I'm gonna call it make fraction constructor, just so we can connect these dots here a little bit. So it's called make fraction constructor. And this guy takes in all the information you need to build a fraction. It internally builds the fraction for you, whatever that means in your setup, and then returns for you that fraction. So now up here, we can do some, instead of saying those 3 lines, we can say struct fraction f2 is equal to make fraction constructor 3, 4. Something like that. Now we just generated a fraction and made it the fraction 3/4. Now, is there anything happening inside of this function down here that isn't happening right here? No, it's just something we might say, you know what, I'm going to be making a lot of fractions. So let me go ahead and build a little function that I can just give 2 values to, and it gives me back my fraction. That's a constructor. That guy's job is to construct fractions. Make sense? So this would have existed in the C programming language all day long. Because as you started using more and more structs, you would have started creating functions to make structs easier to work with. So this is now we're seeing all these extra wires getting attached to our pile of wires version of a telephone over here from our old example. All right. So when we upgraded to an object-oriented language, we had to say to ourselves, okay, well, let's look at our code. And we have all of this, these functions and values that are associated with our concept of fractions here. Wouldn't it be nice if we can take all those things and pull them into a single container? So they're all hidden inside that container. We keep track of the numerator, the denominator. We have our special function for building fractions for us, for initializing and constructing them. Maybe a fraction also knows how to add itself to another fraction instead of having another function that's just laying out there, another pile of wires next to this guy that I throw 2 fractions at it. It throws me a fraction back. Everybody's happy, but still, we have all these abilities for working with fractions, but they're just laying all over the place, right? Creating that mess. So as our programs have been getting more and more complex in here, we're hopefully starting to see that we are building that pile of wires that was the procedural version of the telephone. And we're kind of seeing that, okay, you know what? While that felt cool, as the programmer, I now have to work with that pile of wires, and maybe that's not the most convenient thing in the world. So we have these are, let's call these relatively meaningless words, but I'm going to throw them out there since they are related to object-oriented programming. We have something called encapsulation. Except I got to spell it way better than that. Encapsulation. Nailed it. All right. So encapsulation. Put stuff that would otherwise be laying, let's say put related stuff that would otherwise be laying around making a mess into a single place. So it is convenient to access, yet the mess is more organized or at least out of sight. So the difference between an object-oriented language and a procedural language is effectively go clean your room. Here's a tool to throw your garbage into. Right? I always did that when I was a kid. When my parents would yell at me, I'd just throw everything in the closet and shut the door, put something in front of the door so they can't conveniently open it. Room's clean.
Those first few words of the sentence are word salad.
Oh, are they? I'm celebrating the put related. I related stuff. Put related stuff that would otherwise be laying around making we'll call that close. All right. So you'll often see in the context of object-oriented programming, people talking about this concept of encapsulation, which is no more than throw your stuff in your closet so your room looks clean. Hopefully you don't need to access the stuff that's in the closet very often. You'll regret it later. You could also use the garage tool chest example where you just throw everything in there, and I always end up getting all the tools rusty because I leave them out in the boat in the rain and then take them back in there, and I don't take good care of my stuff, which is why I can't have nice things. That's my wife speaking through me. All right. So encapsulation is something you'll see with object-oriented languages. I'm not going to test you over that or anything, but just a word. All right. So now let's go and look at creating some objects so we can start seeing these things through examples. All right. So last class. So now we're jumping over to Java now. So let me get rid of, this is illegal code in Java. Structs don't exist in Java. Oop. And then we'll get rid of that guy right there. All right. So trick question. What's the output of this Java program going to be? This is related to something we talked about kind of near the end of class last time, so we might have been rushing a little bit. Go ahead. Okay, tell me more. No. Void is a separate lesson, but unrelated to this. Here, I'll go ahead and hit play here real quick. So you get an error. Why did we get an error? Go ahead. Yeah. So it's something we haven't really had to worry about up to this point. I've always mentioned that all programs begin and end with main. So when we were writing our C and C++-ish code, let's say, we didn't have this extra wrapping. We didn't have all this stuff inside of this thing called a class. We just had that main method, right? So that's where everything began and ended, is with main, and then everything else lived outside of main, but inside your program, let's say. So Java brings into existence, everything in Java will live inside of a class. It's a pure object-oriented language. Class is just an organizational tool like we just talked about. But there is a rule in Java as well as C#. So most modern languages have this rule where the name of your class must identically match the name of the file. So in this case, my file name is main.java. I think I mentioned this last class, right? That in online GDB, when you create a new Java project, it defaults the file name to main.java, which I don't like. So if I just put it back here real quick. So now this guy will run. So there's your hello world. Okay. I don't like this example because this main and this main have very little to do with each other, yet they can be confusing because they have the same name, right?
So why didn't it like driver?
It didn't like driver here because the name of my file is main.java. If I want driver to work, I would have to rename this file to be driver.java, which I'm going
I
to do.
see.
All right. But if you were to look at this file by default, if I had just created a brand new project here and with online GDB and selected Java, it would have written it like this, where the class name is main, because the file name it generated for me was main.java. And all Java programs that the program that you intend to run, only one of your classes can have a main in it and have it run. All programs begin and end with main, just like they did in C and C++. But as we start getting into object-oriented programming right now, we're going to start having our program will have several files with several different classes that are involved. And only one of those classes can have a main. Otherwise, Java won't know what program you want to run. Okay. Um, uh, let's call that mostly true. All right. So what I'm going to do here is, because this can be confusing with a class name main and public static void main here, this is the main that we've seen up to this point. This guy that I have highlighted right here. That's the same main as we've been used to in C and C++. This guy is misleading, in my opinion, using the word main. Beginning programmers can get confused with that. I'm going to go ahead and change it to driver. I like naming it driver. You can call it whatever you want, but I typically like naming my class that has main in it as driver because it's the thing that drives the program, right? And we used the analogy last time I asked people about graphics cards or something like that. And what does it mean when it says you must install the drivers for your graphics card? You got to install the software that tells your graphics card how to work. Otherwise, your graphics card will work as a generic VGA, whatever. So in order for this guy to work, I will go ahead and run it again, and we'll look at the error message. It says, error, class driver is public. It should be declared in a file named driver.java. Okay. So we'll just go ahead and rename this guy, which it's nice that this didn't work before. Online GDB used to not allow you to rename their top level file, which was unfortunate, but I'll go ahead and rename it to driver. So now the file is called driver.java. My class is called driver. The capital, it must be capitalized because the file is capitalized. Typically, in object-oriented languages, class names are capitalized. That's a naming convention, not a rule. All right, but usually if you see something with a capital letter at the beginning of it, it's probably a class. All right, so now my class name matches my file name. I go to run this, it's going to run. Everybody's happy again. All right, this is the same main we've been dealing with before. Just to review this real quick and to kind of bring light to what he had said. If we were writing this main in C++, we would say int main. Now we've seen it like that, just int main. I'll go ahead and write the old school thing where we have int argc char pointer argv. These two lines are probably separated by 40 years, but they do the same thing. All programs begin and end with main. This is what main looks like in C and C++. You might want to take command line arguments. Here's your collection of strings. Here's how many of those strings there were. Because in C and C++, arrays cannot report their length. Java, they can. So in Java, I have a string array. Don't worry about the syntax right now, but we've seen these little square bracket thingies. They kind of say array thingies. Okay, so we have an array of strings, a collection of strings named args, arguments, and args.length tells us how many things are in there. That's why we don't need that second variable. Realistically, most of you might go through your entire career and never use command line arguments. Historically, they were super, super common. but we also didn't have graphical user interface operating systems where you just double clicked on stuff. You were running all your programs from the command line. It does still exist now when you do a lot of web development or back-end development where you're writing stuff up on Linux servers, so you're not using graphical user interfaces very often. So you are running your programs from the command line. So it's not that this doesn't exist anymore. It's just not necessarily common. So I'm really kind of telling you about the history of this a little bit. All right, but we're going to go ahead and get rid of our C++ version of this. Although I'll throw one thing out here. You could write this as that if you want them to look a little closer. Modern day C++ does not require main to return a value. Old school did, because that was the value that main returned was like the error code. Did the program run successfully or did something screw up along the way? If so, what screwed up? Depending on what number was returned, error 5 meant one thing, error 6 meant something else, error 7 meant something else. So that returned integer could give us information about whether the program was successful using a return value of 0 meant successful, or a return value of something other than 0 was some sort of error message that you would then maybe have that wrapped in an if statement. If program returns 0, do the next step. If program returns something other than 0, let's give them an error message saying what went wrong and don't continue the program, because step 1 broke, step 2 is not going to work. All right. That doesn't exist in modern languages, that whole return and int thing, because modern languages have new facilities for handling errors. They're called exceptions. We'll look at exception handling at some point. All right, so we'll get rid of our old main. The reason I wanted to bring this up is because he mentioned this program might not do anything because of the return type of void. Okay, remember, void here is what main returns. Whoever calls main, which is going to be the Java runtime or the Java virtual machine, will be the actual guy who calls main, not us. We hit play and something calls main for us. All right, but main does not return a value in Java, therefore its return type is void. Well, you might say, well, why do I have to have any return type in there? You're right. And Java makes some other decisions that seem to support that idea, that if something is always written a certain way, why do you have anything in front of it? Why can't main just be this special thing? Why does it have to be compatible with any other function? Because remember, this generic syntax for a function is return type, function name, parameters. And what I'm saying in Java, for main, the return type is always void. So it would be reasonable for us to ask the question, why did I have to put a return type in there at all? Because in Java, main at the syntax level, the syntactic level, is a function. It just happens to need to be named main in order for your program to work. That's the thing the virtual machine calls. It says, someone out there, I'm calling your main method. Hopefully you're out there listening, and it goes and runs. If you don't name it main, it's not going to work. So at some point you needed a structure. All right, so it's always going to be main. It's always going to be public. That has more to do with like file permissions. And it's always going to be static, and we'll talk about that later. So for right now, let's just assume that your main method in Java always starts off like that. In fact, we can go further and say your main method in Java always starts off like that. We could change the name of our variable in the parameter. It doesn't have to be called args. It could be called elephant if we wanted it to be called elephant. Whatever you name it here is how you would use it in here if you were going to use it. In this case, we're not using the command line arguments. But I'll run this. We see that it still works. Let me check something here real quick. I think there is a way for me to give it command line arguments. We'll see if I stumble upon it at some point. That doesn't matter. I was just going to show you how command line arguments might work. Doesn't matter. Okay. So any questions about that? This is our generic hello world program in Java. instead of C out. So this line right here, this is C out. Hello world. These two lines would do the same thing. Print ln is a carriage return line feed. So that says print this out and press enter. If I left
No need to declare the
go ahead.
no need to declare the namespace.
You do not. You do not. No namespace here. All this stuff lives inside of the generic Java runtime. We will import stuff before long, but there isn't the thing of a namespace. It does exist in Java. They're called packages. But it's not something we're going to get involved with because the normal stuff we're using is all part of the core Java that's imported by default. Typically, that's java.lang. That's the stuff that's built into the Java language. So it's already available to us. All right, so print and println are our two options. So print prints something to the screen and does not press enter. Println presses enter. What's the system.out crap before it? We'll talk about that in more details. But if I'm just connecting the dots to what we're dealing with right here. In fact, let me bring up the documentation so we can walk through it just so you can see, because learning the Java documentation is going to be kind of an important piece here. So we're going to say Java system class. All right, so inside of Java, so let's walk this. We're saying system dot something. Now I mentioned this guy has a capital S in front of it. When something is capitalized, what is it likely in a language like Java? What kind of animal is that likely if it's capitalized? Good. It's class. So more than likely, I mean, this is not a legal rule, but more than likely, when I see the word system there capitalized, bells should be going off that, oh, there is probably a class name out there called system because that's capitalized. Now, when something is not capitalized, that's probably a variable or a function. How do I know that that guy out is likely a variable and not a function? This is something you can rely on your knowledge you've had up to this point. This is not a Java question. This is just a programming question. How do I know that the word out there, if I'm telling you that's not the name of a class, and you can say it's probably not the name of a class because it's not capitalized, and then I'm asking, well, what is out? What kind of thing is that? And I'm telling you it's either a variable or a function. How do I know this guy's likely a variable, or how do I know this guy is definitely not a function? What do functions look like? Specifically at the very end of the function, calling the function. What do they all have in them? Open parenthesis, close parenthesis, with zero or more parameters, right? So if this guy was a function, we would expect it to look something like that, or maybe something passed in there. So the fact that it takes no parameters, the fact that it doesn't have a parameter list at all, tells us that we're probably looking at a variable here, or an object-oriented speak, a field. Go back to our notes here. I said, what is a class? A class is a collection of fields, which are variable names associated with the class, constructors, which look a lot like methods or functions, but a little different. We'll see one here in a minute. And then our normal methods. These are things that we're already used to. They just happen to be stuffed inside of our object instead of floating out in the outskirts. So those are the three things that can exist in there. So I expect this to be the name of a class. I expect this to be the name of a field. What about this guy? What kind of animal do you think that is? Cat, dog, or function? Go ahead. It's a function. Man, we were probably between cat and function. I know it's close. Hey, question or lizard? It's a lizard. Yeah, that would make some sense, especially with the green. So we expect this to be a function because it has all the telltale signs of a function, right? It's got a name, it's got a parameter list with some stuff in there. That's either an error, right? Which is every bit as possible for beginning programmers, right? But, assuming it's not an error, like that guy, it looks like you're trying to call a function. So we have a class name dot field dot function name. Go ahead.
Is that just?
We'll talk about it. It's part of the syntax. It'll make sense, I think, in a minute. So ask again in like 5 minutes if it doesn't make sense. All right. So we've now speculated on what we think is going on here based on just naming convention stuff. I realize most of you've never seen this before, and we haven't even gone into the documentation yet. But this is an important skill to be able to look at code and say, this is the type of animal I'm probably dealing with here. This gives you a lot of information because it allows you to then use tools that you haven't otherwise used because you understand the high level thing of it. If you bring home anything electronic from the store, you kind of know you probably need to plug it in or put batteries in it. It needs a power source. That is a common knowledge that we have because we've worked with electronic devices before. You don't have to necessarily know what the device that's sitting in front of you does. It just has some common characteristics that all electronic devices would have. All right, so let's go and look at this. We're expecting a class name, we're expecting the name of a field, and we're expecting a function that lives inside of whatever this guy is. Hence the dot notation. So I go to my system class here. So here's inside of Java, we have a class called system. We're going to be talking about this here in a few minutes. This idea that system has one parent class, and that's object. Notice it's java.lang.object. All object-oriented languages have a class named something like object. In C++, or I'm sorry, in C#, it's object lowercase o. Java, it's object uppercase o. Now, in C#, that's actually a problem since I've told you that most of the time object names are uppercase. So of course they have the most important object in the entire language being lowercase. Makes perfect sense. All right. So in any case, we have a class name system. I come down to my fields. I find a field in here called out. What is out? He's something called print stream. What kind of animal do you think this is? What is print stream? For most of you, it's the first time you've ever seen it, but what kind of animal is it? I'm not even asking what it does. What are my options? Oh, go ahead. Class name, why? Capitalize. No more than that, right? It doesn't have to be a class name. We just highly suspect it to be because it's capitalized. So we expect this guy to be the name of a class. Java's documentation, I think I mentioned this before, is called Java Doc. Originally, they thought everybody who was a Java programmer would use the Java Doc tool to generate documentation for all their code like that. Nobody does. But their documentation is actually really great. So if you understand how to read Java Doc, which is what we're looking at here, reading the core Java documentation is awesome because it's one of the most well-documented languages that's out there, period. Nobody could argue that. Normal developers who write in Java never use Java Doc, so their crap is not going to be any more organized than some other languages. Some of these older languages like C++ make you jump through some hoops with like header files, but they end up being far more organized than Java programs from normal programmers end up being, because Java programmers don't do the extra hoops and they also don't document their code. I don't either. In any case, let's go ahead and click on print stream here. We're expecting to find a class. It's capitalized. So we found this class called print stream. Okay, going back to our code here real quick. Out is something called an instance of the print stream class. Println looks like it's a function. I expect, and in object-oriented languages, functions are called methods. It's a synonym, just another name for it. So what I expect to find here inside of the print stream class is I expect to find under the methods, remember all classes contain fields, constructors, and methods. That's what makes up a class. So under the methods section, I expect to find something called println. We'll actually find lots of printlns in there. So we scroll down here, we get to the P's. Here's a whole bunch of prints. Here's a whole bunch of, here's our print Fs that I referenced before from C. But here's our print lins. So we have a print lin that takes no parameters. We have a print lin that knows how to print a Boolean. We have a print lin that knows how to print a char, knows how to print a char array, old style strings, knows how to print a double, a float, an int, a long, knows how to print a generic object. We'll come back and talk about this sometime soon. And also one that knows how to print a string. All right. So when we look at println here, it introduces another term to us. We got a fancy term called polymorphism. Another object-oriented term, fairly, call it unimportant in terms of the name, but what it says is when there is more than one method with the same name, but a different number and or type of parameters. That's called polymorphism. So if we go back and look at our documentation here, we see, okay, we have a whole bunch of functions here all named println. So we have more than one function with the same name. This one takes no parameters. This one takes a single Boolean as a parameter. This one takes a single char as a parameter. This one takes as a char array, a double, a float, an int, a long, an object, a string. So we have a whole bunch of different printlns, but they do differentiate themselves by taking in a different number and or type of parameter. That's what polymorphism is. But understand that the variable name does not matter. And let me give you an example of that. Let's assume I had this function println, and this guy's void. Doesn't matter in this example. Println int a, so that's what we just saw, right? Println, oh, it's int x, sorry. So there's the int x in our documentation. Now I'm going to create another println int a. Is that an example of polymorphism? Why not? Polymorphism says they have the same name. Both of these do, right? Go ahead.
Because on the same variable.
Do these guys have the same method name? They do, right? They're both called println. Do they both take the same type of parameter? They do. So they do not take a different type. They also take the same number of parameters, right? So both of these guys take a single input. They take the same type of input. That immediately disqualifies it. This is illegal. You cannot have two functions that have the same name that take the same number of parameters unless those parameters are of different types. In this case, they're both ints. Yes, one's named X and one's named A, which might be meaningful to us. Java doesn't care. These both are functions named println that takes a single int. Make sense? So this would be illegal. You couldn't write it like this. So our example of polymorphism that we see inside of the print stream class here is that we have a whole bunch of functions called println that take either a different number of parameters. Here's one that takes 0. Here's one that takes 1, or a different type of parameter. All of these have unique types. And here's our catch-all, println for an object. And we'll talk about that here, if not today, then on Thursday. That's kind of our catch-all since we're going to be inventing our own objects. So if we're going to invent an object called fraction today, how does this println that was written a while ago know how to print something that we just invented today? Well, the documentation says it does. So let's actually see that. All right, but before I go any further, do we understand how I walked through the documentation here? It's going to take practice for you to do that, but walking through this documentation showed us where this all comes from. Class name, field name, method name. Why the dots? We have a class name who's going to call one of his fields. The way he references something that belongs to him, just like we did with structs, is we use a dot notation. System dot out. Just like with a struct, we had a struct F1 and we said F1 dot numerator. Similar thing. Okay, so we have system, call this guy that belongs to you. He's a field. Why? Because it doesn't have a parameter list and it's lowercase, probably a field. And then that field, this guy's an instance of a field. We'll talk about that soonish. He's going to call something that lives in him, which is a method. So this guy will call his own function, which is why we have the second dot, outs dot. Out dot println is the println function that belongs to our instance of print stream named out. All right, so questions about the documentation here. Go ahead.
So for calling, what would be the, like, well, so he's trying to understand, what, yeah, what would be a polymorphism, print line?
So this guy here is illegal because Java could not tell the difference between these two. They both have the same name and they both take in the same type of parameter and the same number of parameter. Does not matter that the variable names were different. But this one is an example of polymorphism. This is called println, just like this one is. He takes a single parameter just like this one does, but the type of parameter is different. So Java would be able to differentiate which of these guys you mean to call by the way you're calling it. If you called println and you passed it a double, it would know that, oh, you mean the one of these for double. And he'll call that version of it himself. Java does that for you. It figures it out. But in order for Java to figure out which function you meant, the functions need to be mutually exclusive. You need to be able to tell them apart from each other. And as far as Java is concerned, these two functions are indistinguishable. They are the same function from Java's perspective, even though a human being may have noticed that one of them has a variable A and one of them has a variable X. They're the same type. Java's not that smart. Got it? All right. Here, I'll put a little statement here, not allowed. All right. So now let's just look at an example. So let's go ahead and write our class. Now, what I'm going to do here, I'm going to start off by writing my class in the same file, because at this point, we've always written all our stuff in a single file. But real quickly, I'm going to be moving this out of this file. But let's just keep it as simple as possible. So I'm going to create a class called fraction. And we're going to say that a fraction is going to have an int numerator and an int denominator, just like that. So at this point, that guy kind of looks like a struct, right? We look at this in those guys basically look the same. Little bit of a syntax difference, but at a glance, it's the same kind of thing, right? Java would agree with that statement that, oh, a class with no functions or constructors is basically a struct. It's almost a struct. We'll see why here in a second. If going back, let me just write something here. It won't run, but if I say struct fraction F1, and then I said cout F1, I'm not going to get a memory address there. Because structs will probably get an error. But structs are by default passed by value, not passed by address. But what if, let's go ahead and get rid of this struct syntax. So structs don't exist in Java. So you can say goodbye to structs for right now. Get rid of this guy. And I'm going to go ahead and I'm going to create a fraction called F1. Now, if I go and I say system.out.println F1. So I created a fraction F1 and I'm printing it out. What do you think is going to print? Gives us a warning. Well, it says an error, but it's really a warning. It's saying variable F1 may not have been initialized. You may not have given it a value. All right, well, so what if I say F1.numerator is equal to 1, F1.denominator is equal to 2. F1 may not have been initialized. Well, didn't I give it my numerator and my denominator? What is F1? What kind of animal is F1? Cat, dog, or variable? It's a variable. What's a variable? Generically speaking, what is a variable? What does it do? A variable is a named location in memory, right? So we've created a variable named F1. If we had a special syntax in Java for looking at addresses, and I were to instead say the address of F1, so if we just pretend for a second we're still swimming in some C++ infested waters, all right, and I were to try to print out the address of F1, it would give me an address. This doesn't work in Java because that syntax doesn't exist in Java. Remember, I mentioned Java does not have special syntaxes for working with pointers. Pointers still exist. We're going to see a memory address real quick. All right. But if we were working in C++ here and I said, I want to print out the address of F1, it will print out an address. But what is that address? What's the address it would be giving me? The address of what? Remember, we said with a variable, F1 is the name of a variable. What is a variable? A variable is a named location in memory. So the address of F1 is where in memory is that named location. It's not the value that lives in F1. As it's yelling at us, we didn't actually put a value in F1. We said, Java, I want to create a named location to store a value. And I want it to be able to store a fraction. Java said, no problem. I'll just set you aside this little place in memory here for you to put your fraction in. And here's your variable. I don't have a value. Remember, variables are name value pairs. Right now I have a name and I have a location where the value would be stored if I had a value. The address of F1 would be that location. But Java doesn't let us reference it like that. Okay, so we can't actually get to that in Java. Not the end of the world. There probably aren't really good examples of when you'd want to get at that legitimately. Java does the work for us. But right now, even though I tried to set F1's numerator and F1's denominator to 1 and 2, it's still telling me it wasn't initialized because numerator and denominator are components of an actual fraction. I don't have an actual fraction yet. What do I have? I have a container that knows how to hold a fraction. So I have this little shoebox here that I've labeled as being capable of holding a fraction. I've named that guy F1. It's got a nice little place on my shelf right here. Here's the memory location, right? But there is nothing in that box. That is an empty shoebox. And I'm trying to say, well, okay, that empty shoebox, that nothingness, I want you to set your numerator to 1. So we're telling nothingness to set its numerator to 1. That's nonsensical, right? We're talking to the wall. We're talking to the empty box. Okay, so if it let me pass this line, we would get what's called null pointer exceptions. Because in this case, variables, we've said it before in C++, variables resolve to their most local definition, right? So F1 will resolve to a value. What value? The value stored inside of F1. What value is currently stored inside of F1?
Nothing.
Nothingness. Nothingness. So if I were to replace F1 here with the value it would resolve to in Java, that value is null. So I'm playing the game of resolving it for you. So if I were to resolve F1, like right here, F1's current value is nothingness. And nothingness in Java is spelled N-U-L-L, null. Some languages it's nil, N-I-L. Some languages it's null with a capital N. Ooh. That pretty much covers it. I think they're all either nulls or nils. There's probably another weird one floating out there somewhere. All right. So when we look at it that way, when we use our mind and say, okay, well, let's resolve our variables. And then we say, okay, well, nothingness's numerator is 1. That stops making sense to us, right? Understand the difference here, though. When you glance at, if I remove that line right here, and I just say fraction F1, F1 dot denominator, when I just glance at that, everything looks like it could reasonably be okay. But when we stop ourselves for a second and we start reading the code, important skill for beginning programmers, because it's so easy to glance at this and say, oh, that looks pretty good. But when I actually resolve it and say, well, what is the actual value of F1? In this case, the actual value of F1 is nothing. And if I try to have long conversations with nothing, I'm not going to get real far. So this immediately looks pretty suspicious when I'm asking nothing to set one of its values to something. Make some sense? So how do I get F1 to hold something other than nothing? That's the kicker. Well, we would say F1 equals a new fraction. Like that. But now let's look for a second. Even though I'm eventually going to put this guy in its own file, right now I just have it up top here. I'll explain kind of why that works later on. But you know, trust me for right now. This guy right here looks like what kind of animal is that? Is that a class name? Is it a field? Is it a method? What does it look like? What does it look the most like to you right now? We immediately go ahead. Function-y thing, right? Why? Because we have the open close parentheses. Okay, it's not where we don't have to be deep thinkers here. We look at it, we say, oh, I see a couple of parentheses here. That is something along the lines of a function. Then I look at it and say, oh, okay, wait a minute. This guy's capitalized. Well, when we've already talked about when something is capitalized, that lends us to think that that's related to a class, because class names are typically capitalized. So when I see something that looks like a class name, but it also looks like a method, that guy's probably a constructor. Constructors have the same name as the class that they're in. So the constructor for fraction is a special kind of function. We'll differentiate that a little bit more here in a second, with the same name called fraction. Now, if I run it just like this, oh, sorry, I got my illegal pointer syntax in there. We see that now we get an answer. Now, let me ask you something. Does this look memory addressy? Kind of hexadecimal type value? It says fraction at before it. Java runs inside of something called a virtual machine. So Java creates its own kind of like micro operating system. So it has its own memory manager. And Java says, oh, okay, here's the actual memory address. And this is the fraction that lives at that memory address. This is what prints out when I try to print that memory address. And I'll talk about the rationale why probably next class, but pretty quickly we see memory addresses, right? Pointers exist. We see memory, pointers exist. But when I look up at my class called fraction here, did I write that? Did I write any function in there called fraction that takes no parameters? In modern programming languages, if you don't explicitly create your own constructor, which we didn't here, right? And here we basically just made it like a struct. Java will provide one for us. It'll provide a constructor that takes no parameters and does nothing. The reason that exists is it has to support this syntax right here. Remind me, what does the new keyword do? We've had the new keyword in our notes already from C++. What's that guy do? What's his job? He's one job in the world. Okay, I referred to him as our real estate agent. He goes and gets memory. Whenever we see the new keyword, he goes and gets memory. New is the less scary version of malloc, right? We are allocating memory in C and C++, asking the operating system for this number of bytes. New is the more modern version of that. And he just says, look, you tell me what you want to build, I'll take care of the amount of memory you need. So the new keyword has to know what he's building. So if you didn't explicitly write a fraction here, or write a constructor, it will provide one for you. So we saw the memory address. But if I go in here and I say fraction, int numerator, int denominator, like that, and then I run this code again, now it's going to yell at me saying fraction in class fraction cannot be applied to the given types. I'm trying to call a constructor that takes no parameters. Yet I have chosen to write my own constructor here, one that takes 2 parameters. So because I've stepped in and I've written my own constructor, notice constructors have the same name as the class, and also notice they do not have a return type. So they're a lot like methods, but constructors don't have a return type because they are always used after the new keyword, which means that they would always return a memory address, which means you don't have to explicitly say that. It's what it does. But because I wrote this guy myself, Java no longer gives me a no argument one. It says, okay, you must know what you're doing. So now it's yelling at me again. But if I were to call this guy with like 1/2 like that and run it, now it'll work again. There's my address because I did indeed call my constructor that takes 2 parameters. Sure, it does nothing, but I still called it. All right. All right. So we're going to stop there. Next time I'm going to come in, we're going to be talking about the this keyword. We'll just throw that in the notes here. So I'm not giving you a specific assignment, but start practicing converting some of your stuff over to Java. I'll just say start here. All right, questions, comments, concerns, bribes. Okay, pretty important this lecture and the one after this to kind of close the gap on some of these things. So go back and watch through it. There's a lot of like kind of trivia information in here that isn't important to memorize, but it's important to understand the structure of what's going on here because that's understanding that structure basically opens the entire language up to you. All right, so spend some time looking at that. The this keyword is not difficult, but it's going to fall into that same category as pointers where it's going to be difficult to wrap your mind around initially. All right, I'll see everybody on Thursday. Might be a little slow communicating tomorrow. I have my hopefully last back surgery tomorrow. So maybe I won't reply to anything till like after 3 p.m. So give me a little bit of leeway.